Good morning all. So last class we have discussed about PAM modulation. It's how it is generated, different sort of problem we have solved with respect to sampling theorem. Okay. So today we are going to discuss about PWM signal. PWM and PPM is left in the module 4. Next we will discuss with respect to our quantization theorems or quantization procedure. What is quantization? That is the last part. And in that quantization, how many type of quantization? What is the quantization noise? And the different type of quantizers are available through which the signal can be enhanced. Okay. So depend upon this generation and all. First we will discuss today. The date is 18, 12, 2020. So today we are going to discuss about the demodulation. Last class we have seen how many type of samplings are there. Even the flat top sampling is also called as PAM modulation. So I am not discussing that PAM once again. Today we will discuss with respect to the demodulation. Demodulation of PAM signal first. Okay. So it is a demodulation. Demodulation of pulse amplitude modulated signal. Now the question comes, why it is called as modulation, why it is called as demodulation? Now modulation means we require a message component, we require a carrier component, and the carrier characteristics is changed with respect to the modulating signal. Then only it is called as modulation. Okay. But in sampling, what happens? The modulating signal are sampled at a different interval. Different means at a equispaced interval for a sampling time period Ts, with variation of amplitudes. Okay. Like it is having instantaneous sampling, it is having flat top sampling, it is having natural sampling. Now natural sampling, after some sort of this quantization process, we will get the discrete value. If it is instantaneous, we will get the discrete value at the one step further. But if it is a natural sampling, you need to quantize it, and then the instantaneous sample signal is equivalent. That is called as our discrete signal. That is, whole process is called as a discretization. Now here, that pulse train which we are going to use to sample our modulating signal, that pulse train acts as a carrier component. We are changing the characteristics of that particular impulse train. The impulse train what we have used, it is having a constant amplitude, that is 1. Okay, impulse train. Periodic impulse train with a uniform amplitude 1. Now when you mix this modulating signal with this impulse train, the amplitude of this impulse train is going to change. So if the amplitude is varying, that means it is called as a pulse amplitude modulation. Okay. Now how this PAM signal is generated? First, the instantaneous signal is generated. Okay. Instantaneous pulsar sample signal is generated. To that impulse, you are multiplying one pulse. Means after the instantaneous sampling, we will get this sort of discrete value. Okay, for positive half as well as for negative half. This is the instantaneous sampling, that is x of n. This is t, this is 0, this is ts, this is 2ts, this is 3ts, this is 4ts, this is 5ts, means time period, not amplitude, this is 6ts, 7ts, like this. So this particular instantaneous sample is generated after the instantaneous sampling. Now in flat top sample, what happens? I will consider a rectangular pulse. We have already derived how the mathematical expressions are related with respect to the figures. Just I am discussing this because we have to discuss the demodulation technique. Okay. Now this particular pulse is having a certain amplitude A. Let us consider for a time period of minus plus d by 2 to minus d by 2, and this is the pulse. Now this pulse whose top one is flat with a constant amplitude, when you multiply this one to the each and every position, the resultant you will get, this is the first sample, so this pulse is here. This is the second sample, the pulse is here. Okay, this is the third sample, the pulse is multiplied to this particular group. Then this is another sample which is going down. Then again there is one sample, and similarly for the negative half also you can consider this value. Now this signal, what we are getting after mixing this instantaneous sample signal and pulse, your resultant you will get as a Pwm signal. It is a pulse amplitude modulated signal. So pulse amplitude modulated means the pulse amplitude was changed according to the given information. Now this is my modulating signal. This is the carrier component you can consider, whose amplitude is going to vary with respect to this signal. So amplitude is fixed. Now when you multiply this one to this, its amplitude is only going to change. Pulse time period need not to change. Pulse time period remain as it is. The width of the pulse remain constant. You can see the pulse width of these pulses are same. Pulse width means this point to this point, this time to this time, this time to this time, this time to this time, this time to this time. Neither the time period change of a particular pulse, only the amplitude is changed. If the amplitude of a pulse is changed with respect to the given input signal, then you can say it is called pulse amplitude modulated signal. Okay. So this is the basic analogy behind to generate the Pwm signal. Now we need to demodulate it. There are two different methods are available. One is holding circuit and one is equalizer. Okay. So zero order equalizer I can say. So first we will discuss about the holding circuit. Okay. So there are two types of demodulators are available. One is holding circuit and one is zero order equalizer. These are the two methods through which if the Pwm signal is received, we can bring back to the original modulating signal. Original modulating signal means the modulating signal is look like this. Okay. This is my modulating signal. So from Pwm to modulating signal, the process is called as the demodulation of Pwm signal. That we can do with respect to two methods. One is holding circuit and one is equalizer. Okay. So first we will discuss about holding circuit. It is called the holding circuit is nothing but a switch followed by a capacitance. It is a small circuit through which the Pwm signal can be generated. Let's see how to generate it. So the basic block diagram is, first the received Pwm signal enters to the holding circuit and output of this holding circuit is fed to the low pass filter to reconstruct the original modulating signal. So this is my M of t and this is my pulse amplitude modulated signal. Now what is this holding circuit? The holding circuit is nothing but a small switch which is switch on and switch off at a regular time period of Ts because it needs synchronization. Okay, synchronization of what? Synchronization of a sampling time period in which the samples are generated. We need to synchronize it. Okay, so time period Ts and parallel connection with a small capacitance C. Small capacitance C. So at this point we are providing Pwm signal, and this point we are getting modulating signal, but it must be followed by an LPF. LPF means again it consists of series combination of RC circuit. Okay, so output will fit to this particular LPF and we will get our modulating signal. Modulating signal. Done. So this is the small circuit, but how it operates, let's see. Okay. So let us consider the pulses what we are going to receive. Let us consider this is the pulse we are receiving. So the pulse starts from here. Okay. This is another pulse. This is another pulse. This is another pulse. This is one more pulse. This is the negative component in a negative half cycle, and this is another component. Okay. So this is my PAM signal which I am going to feed to this holding circuit, and this holding circuit is having a switch followed by a capacitance. Now what is the principle of this particular circuit? Let me discuss first. First, the switch remains closed when the first pulse is received. So when the first pulse is fed to the particular circuit, it will become closed. Okay. After that what happens? After that you can see there is no pulse between first pulse and second pulse. Let me notify it. It is pulse 1, pulse 2, pulse 3, pulse 4, this is 5th pulse, this is 6th pulse, 7th pulse, and this is 8th pulse. Okay. So when the first pulse is received, that means this time period, this switch will remain closed for that particular time period. So when it is closed, the potential drop will be taken place for this particular charge, and capacitor will charge up to the potential what this particular pulse has. So it will hold a particular potential for certain time period until unless new potential is provided to it. Okay, that is the principle of a capacitor. Now when let us consider here the potential is around 1.5, here the potential is around 2, here the potential is 2.5, here the potential is, let us consider it is to 1.8, okay, and here it is 1.4, here it is negative components are there, or let me represent it 1.8 minus 2.5 and this is minus 3.0, like this. Some amplitudes are assigned, randomly we have assigned. Now when this 1.5 potential is observed in this particular switch, the switch will close for the time period that Ts. In that time, the capacitor will hold a particular potential that is 1.5 until unless if another potential is reached. Okay, so 1.5 will be holding by this capacitor. Then what happens? When it is totally get charged to 1.5, the switch will automatically switch off. Means it will just as an open circuit. If it is an open circuit, there is no potential available between these two pulses. Okay, till this much, this capacitor will hold the potential 1.5 till this particular time period. Okay, because when it is switched was off, the capacitor will hold the particular potential until the next pulse is reaches. Now next pulse when it is reaching, again the switch will be closed and the new potential is added, that is 2. Okay. Now initially we have 1.5. Now we are receiving 2. So what is the difference? How much the pulse must increase? The pulse must increase by 0.5. So what will happen? He will compare the received potential with the potential available with the capacitor, and then he will decide whether we have to increase the potential or we have to decrease the potential. So here it will increase the potential. Okay, so that I will draw yellow lines, you can see. So from here it will hold the data, okay, until it reaches to the 2.0. Then again same method is happened. Then from 2, when 2.5 is reaching, that means we have to increase 0.5 and it will go out. Similarly, when it is having 2.5, it will wait up to the next potential, and then if it is 1.8, then the decision will be that you have to decrease 0.2 potential from the 2.5, or you have to decrease some 0.6 or 0.7. 0.7 potential you have to decrease it. So it is decreasing. Similarly, this will hold up to the next potential. Similarly, it will hold up to the next potential. Similarly, it will hold up to the next. Similarly, it will hold up to the next, and then this. Okay. So here you can see the potential what we are getting. It is in terms of edge to edge connection. This is edge to edge connection. Like this it will come. My drawing is not so good. It will come as a edge to edge connection. Means the resultant output what we will receive, it look like this. So this is the first step. This is the second step. This is the third step. Then this is this fourth step. Then this is the fifth step. Then it comes down, sixth step. Then this is seventh step. Then this is eighth step, and then it ends. Okay. So this is my output of a holding circuit. Output of holding circuit. Now when this output of holding circuit with respect to time, these all are time pulses. Okay. Now this is the output of holding circuit. Now when this output is fed to the low pass filter, the low pass filter will identify the edge to edge and reconstruct the original modulating signal. Edge to edge means it will check like this. This is the edge to edge connection. Means peak to peak values are there. This one. And the output of LPF will be in this particular manner. This is T. And this output of LPF is quite similar to my modulating signal. So the modulating signal was reconstructed. So this is the step 1. This is step 2 and this is step 3. In step 3 we are getting the modulating signal with the help of what? With the help of this holding circuit. First it will hold the potential. Second, after getting the output of this holding circuit, it will enter to the low pass filter. The low pass filter will help to reconstruct the original modulating signal. That is, this is our original modulating signal. So this is the basic principle of the holding circuit. It is also called as a demodulation of PAM signal. Demodulation of PAM is done with respect to the holding circuit followed by LPF, or it is also called as a zero order holding circuit. Okay. So this is the basic representation theory. No need to worry, I will provide it. Only paragraph 1 paragraph is sufficient for this. But you need to understand how we are extracting the data. First, PAM signal enters to a holding circuit. Holding circuit is nothing but a switch followed by a capacitor. When the switch is closed, capacitor will charge up to the potential what a particular pulse had until unless new pulses received. Till that time period, the capacitor will hold it, so that it is called as a holding circuit. Okay. Next we will discuss about the equalizer. This equalizer plays a vital role. It is also a small block diagram that I will discuss now. Next is equalizer. Equalizer is also very simple network or a small device through which we can extract the pulse amplitude modulating signal from the pulse signal. Now this equalizer is specifically meant for demodulation of flat top sample signal. It is specially identified for the equalizer because in flat top sampling, or you can say generation of a pulse amplitude modulated signal, we followed a step. First step is modulating signal is used. Then step 2, the impulse train, that is summation n is equals to minus infinity to infinity del of t minus nts. Okay, that is del of nts. Like this I can write, or some impulse function you can put, but the impulse response will be in this particular manner. Next, step 3, you need to multiply this two, and then you need to convolve it. If it is multiplication, you need to analyze in terms of frequency domain to get the spectrum. That we have done already. But just I am discussing what happens in flat top sample. First, modulating signal, impulse train. In step 3, we will get the discrete signal. That is m of t multiplied with summation n is equals to minus infinity to infinity del of t minus nts. If you multiply this, you will get n is equals to minus infinity to infinity m of t minus nts. It is a sample signal, okay, instantaneous signal. Now to this, step 4, we are using a rectangular pulse. That is called a rect of t by t. This pulse, and this rectangular pulse is multiplied to this instantaneous sample, and at the step 5, we are getting the pulse amplitude modulated signal. So how many steps are there? This rectangular pulse you can consider P of t. Okay, this P of t is multiplied with, let us consider this is x of t after sample signal, x of nts. This one I can write x of nts, that is equals to m of t minus nts shifted. Now x of nts is multiplied with P of t. Okay. Now you are generating the PAM signal. PAM signal is nothing but multiplication of this with respect to pulse. Now the equalizer, what you do? You are receiving the PAM signal. Okay. Here, what he will do? He had 1 by P of omega. Okay. 1 by P of omega. 1 by P of omega is a transfer function of a particular filter. This is also one filter. Okay. Now here, when I will convolute these two, let us consider this is our g of t we have got. G of t is equals to n of ts is equals to this much, and the PAM signal is g of t into P of t. I need to remove that pulse so that original signal can be recovered easily. PAM signal, equalizer means it will equalize your signal. It will remove the rectangular function. Okay. So this is PAM signal. When I am receiving, it is, I will not write it is a PAM. I will write holding followed by 1 by P of omega. It will remove that one and you will get 1 minute. This equalizer is having a response 1 of P of omega. Here I am providing the Pwm signal. Okay. In this, when I will take the convolution of G of t and convolution of P of t, it will become G of omega into P of omega. Here we are convoluting this two. Okay. Pwm signal is a convolution of G of t and t rectangular pulse. So, if this is the convolution in frequency domain or Fourier transform, you will get G of omega into P of omega. You need to extract, you need to suppress that rectangular pulses so that the original signal can be recovered. So here, this P of omega you need to synchronize. You need to synchronize. How it is synchronized? With the help of an equalizer. Equalizer is a system, or it is a, you can say it is a device whose response is same or it is inversely proportional to the rectangular pulse. So that rectangular pulse can be removed and we can extract the original modulating signal. So when I am giving G of omega into P of omega here, so G of omega into P of omega, when it is provided to the equalizer is having 1 by P of omega, it will be divided and here you will get G of omega, and this G of omega is nothing but G of t. Okay, so this is G of t, and this G of t is the discrete signal. Here you can see when it is passed through the low pass filter, it will reconstruct your modulating signal. So this is the basic analogy behind your equalizer. Why it is called equalizer? Because it equalizes with respect to the rectangular function. What equalization he is doing? He is taking the response inversely so that we can remove that pulse. We can remove that rectangular pulse and original message signal can be reconstructed with the help of your LPR, which is band limited to the FM signal what is our modulating component is having. Okay, so these are the two demodulation process for our Pwm signal. Next we are going to discuss about the PWM generation. Okay, so now we are going to discuss about the pulse time modulation. PTM means it is called pulse time modulation. Okay, so Pwm we have seen, suppose this is the pulse, it is having two characteristics, one is amplitude and one is time. Okay, now if the amplitude is varied with respect to the given components, then we will say it is called Pwm. If it is Pwm, its position is not changing as well as width is also not changing. The position means if this particular pulse after Pwm modulation it remains constant at the same time period, and for the certain pulse width if it is remain constant, then it is called as a Pwm signal. But if suppose this is the position, it got shifted to this particular position after modulation. Okay, after modulation the pulse shifted to this particular position. Now this sort of thing we will say it is called PPM, in which amplitude will remain constant, pulse width is also remain constant, but it changes its position. So position of the pulse is changed. So that is called PPM signal. Next we have PWM signal. In PWM, position is not changed, but the width is going to change and amplitude remain constant. Means, suppose this is the pulse width. After modulation, if the pulse width is like this, if the time period increases, frequency reduction takes place. and amplitude remain constant. This is called as our PWM signal. This is called as our time signal. So now we are going to discuss about the pulse time modulation. Pulse time means according to the given message signal, the time period of a particular pulse is going to change either with respect to position or either with respect to width of a particular pulse. So first we will discuss about the pulse width modulation, then we will discuss the pulse position modulation. So pulse width modulation means, let us consider this case. There are three cases are there. How to generate the PWM signal. This is pulse. This is my modulating signal. Okay. So in the first case, what I have to, this is my pulse. According to the pulse, according to the message signal, the pulse width must change. So there are three concepts are there. First, either we can go with respect to the leading edge component, second with respect to the trailing edge component, and third with respect to the center of the component, center of the pulse component. Okay. So here you can see this is my modulating signal. Now in PWM, what happens when your amplitude of a modulating signal increases, the width of the pulse will change. Okay. When the amplitude of the modulating signal decreases, then also width will change. But how we will decide for whom width will increase, for whom width will decrease? The thing is, when the modulating signal increases its amplitude, when the modulating signal follows the maximum amplitude at this particular time period, your pulse width will increase. When it is going to be in a negative half cycle, your pulse width will decrease. Okay. So here, this is the leading edge, this is the trailing edge, and this is the center edge. Okay. Now here we have identified 2 points, point A and point B. Point A is the maximum point achieved by a modulating signal, and point B is the minimum point achieved by the signal. Let us consider these are the three lines. This is the leading edge, this is the trailing edge, and this is the center edge of a particular pulse. So according to these positions, the width can be varied. So here, this is the trailing edge. So you can see the modulating signal increases. If the modulating signal increases, your pulse width increases. Okay. So this is the first case. Only for one pulse I am considering. The pulse width increases. It will increase. It will increase up to this much when it is having the maximum. Okay. This is the position. It will increase. Similarly, when it is decreasing, it will, the pulse width become less. The pulse width varies. If the width of the pulse is varied, that means it becomes as a pulse width modulation. Amplitude of these two pulses remain constant. Here, actually it is a leading edge I have discussed, and that is within this particular pulse we have to consider for the first one. So this is the case. Second, if it is a trailing edge means from this particular point we have to consider. So since at this point the amplitude of a modulating signal is achieving a maximum, the width will be identified from this particular point. So this is the width of the pulse. So here pulse width gets changed because here it is reducing, the pulse width is changing. Similarly, here the pulse width is from minimum to maximum, it is increasing. So here you can see again from the trailing edge the pulse is available. Similarly, from the center of the pulse also we can identify. This is the center pulse. From the center position we are identifying the pulse width. So these are the three cases through which your pulse width can be monitored. If the modulating signal amplitude is increasing, your pulse width will increase. If the amplitude of a modulating signal decreases, your width of the pulse is going to decrease. Okay. Now we will discuss the PWM generation. We have a small circuit with the help of the 555 PWM signal. Okay? It is 7, 6. Both are sorted. This is 2, 5, 3. 3 will be output at 5 is the modulating signal we are feeding. 2 is the trigger pulse, means pulse we are trigger pulse. 8 and 4 both are provided to PC, and there is a resistance followed by capacitance. Here it is 1, it is sorted. This is capacitance RC, and here it is provided with potential which is okay. Let me write few points, then we will discuss. It is a monostable multiplicator configuration. Second, modulating signal control the triggering pulse. Then control voltage is about 2/3 of DC. Then modulating signal change the control voltage and to threshold potential or threshold voltage, and as a result time period change to capacitor threshold potential. Okay. And then at the last we get Pwm signal from 3. Now here you can see this configuration, that is a 555 timer which operates in a monostable multivibrator. Okay, monostable multivibrator means in different mode it can be, only in one stable mode it can operate. Now here from the pin number 3 we will get the output. Point pin number 5 is called as modulating signal. This modulating signal is going to control the triggering pulse. Triggering pulse means here the pulse will be provided continuously. Okay, here the pulse will be provided, trigger pulse, and the modulating signal is this. This modulating signal controls this particular pulse. Yes, it is controlled. In the previous figure we have seen, if the modulating signal increases, your weight of the pulse is going to change. It will increase, frequency component reduces. Similarly, when the amplitude of modulating signal decreases, the width of the pulses decreases, either with respect to leading edge, either with respect to the trailing edge, or either with respect to the center. Okay. Now this modulating signal governs this particular triggering pulse. Now, how to increase the pulse width? This is the pulse for a particular time period. Now internally this IC is having a certain control voltage. That control voltage is about 2/3 of VCC. Okay, 2/3 of VCC. Now your modulating signal control this particular potential 2/3 of VCC with the help of what? With the help of a potential drop across R and C. Now this R and C plays a vital role. If this R and C, if I will take a product, then I will get as a time constant. If the potential drop is more, capacitive value increases, time period increases. So when the potential will increase, when the modulating signal increases. When the modulating signal increases, the potential drop in this particular capacitor is high. If this capacitor potential is high, that means capacitive value is high and the product of R and C is going to high, that means time period will increase. So width of the pulse is increased. Okay. Once again I am repeating the thing. When the modulating signal increases, it will control this particular IC. It will control this trailing pulse. Okay, pulse train or triggering pulse you can say. It will control. How? It is having a certain threshold potential 2/3 of VCC. Okay. Now this particular pulse is having a certain time period T. Let us consider T. When the modulating signal is increased, the maximum potential drop across C. So it will identify the maximum potential, due to which capacitive value will increase, and due to the capacitive value increases, your RC value will increase. Okay? If the RC value increases, your time constant tau increases. So the pulse width increases. So if it is T, it will T plus tau, so time period of that particular pulse will increase like this. Similarly, when the modulating signal is coming to the negative component, the negative pulse or the minimum potential, your capacitance will achieve the negative potential or the minimum potential, due to which capacitive value reduces. If the capacitive value reduces, your RC time constant reduces. If the RC time constant is reduces, the width of the pulse is also going to reduce. So if I am changing the width of the pulse, then it becomes as a pulse width modulation. So here two points are there. Modulating signal controls the triggering pulse. Yes, it is controlling. Control voltage is about 2/3 of VCC. This is internally controlled. Okay. Internally potential, threshold potential is this. Third, modulating signal change the control voltage to the threshold voltage. Yes, because some potential drop is there. It will increase beyond 2/3 of the VCC. Potential drop will be in capacitance, due to which capacity value increases, RC component increases, time period increases, the width of the pulse is going to increase. Next, time period change due to the capacitor threshold potential. Yes, if the potential of the capacitor increases, capacity value increases. If capacity value increases, time constant increases, the width of the pulse is going to increase. Similarly, if the capacitive potential is less, the potential available in the capacitor is less, capacity value is also less. If the capacity value is less, RC component value is also less, due to which the width of the pulse is reduces. Okay. Last, and at the output we will get the pulse amplitude modulated signal like this. Pulse amplitude modulated signal. Then if you join this, it will be used as your modulating signal. Okay. Sorry, it is not a PAM signal. Here we are generating as a PWM signal. So here the pulse increases like this. When it is going to be down, the width of the pulse increases. When it is increasing, the width of the pulse increases. So this is called as a PWM signal. Okay. So this is the generation. Next class we will discuss about the demodulation of PWM signal and generation and detection of PPM signal. Okay. For the time being, we will wind up. Next class we will discuss about the PPM signals. Okay. Thank you.